Yeah, welcome back everyone to the penultimate session today. And we will start with a presentation on outreach by David Barney. Please.
Thank you. It's really an honor to present the outreach at ICHEP 2024. In fact, I was involved in setting up the very first outreach session at an ICHEP, which was back in 2012. And at that time, we had one session, which lasted one morning, with about 20 attendees, even though the first speaker was the Director General of CERN at the time. So we've come a long way since then. And this time we had 3 parallel sessions with about 35 to 60 people each time. Poster sessions, we had a big panel discussion as well. So I'd really like to take the opportunity to thank Yirji, Barbara, and Aldrich who made this possible. It was more than we hoped for. And I'll try and run through quickly some of the highlights from these sessions. And I'll start with the bottom line, so taking inspiration from Leah's talk yesterday, start with the main messages. The first thing is everyone should be involved in education and outreach in some way. Okay, it can't be done by just a few people, and it's really encouraging to see there are lots of people already involved. This is great. The second thing, a big message that came out throughout the sessions was that education and outreach activities done by us benefit us as well. So we get to be able to explain our physics, our engineering much better than we would otherwise do so. And thirdly, it's really good if there's some support and encouragement from the hierarchies for doing these activities. So I'll give you some brief highlights of the parallel sessions. So the first thing that came up was overall strategy. So some experiments such as Pierre-Auger, June, they're really just at the beginnings, not quite the beginnings, of their outreach efforts. So they really showed us what the strategy was, physics beyond colliders as well. And they showed that many of them focus on social media, but not only social media, and many other things. So for example, in China, there's a big focus on a collaboration with a printed journal, a scientific journal, that is proving to be very useful. The overall message from these was that outreach has many benefits, builds public appreciation, aids financial support, and inspires young people. So all things we need for the field to progress. A couple of highlights from education. So there are lots of imaginative ways to educate people, from a university class teaching astronomy through the physics of science fiction, which was quite novel. We hadn't seen that before. With peer-led activities as well, so young people teaching other young people. This came up in multiple talks that we had. Indeed, in one of them, an initiative in Germany really focused on quite young high school students, 12 to 16, before they've made the choice of what they want to do in their later years at school and then on to university. And they were getting these young people to actually lead activities such as cloud chamber workshops. So indeed, these imaginative and peer-led activities are really valuable, they're really beneficial to everyone. Other educational activities included open data, which many of you know about. And this can reach thousands of people worldwide to actually look at our real data. And lots of people are very excited by the possibility to be able to do that. We had 2 highlights. One was Atlas, one was Pierre-Auger. Atlas mentioned that actually the things they've developed are useful for new Atlas physicists as well, not just for the people outside. There's a Czech program as well that aims to incorporate analyzing real data into their school activities and university activities. So they reach thousands of people, but there are also activities that reach tens of people that are equally valuable, because then those tens of people spread the message further. So there's a couple of examples, one with the Ukraine-US program of master classes and bringing people from Ukraine to work with CERN physicists, or the Italian Inspire program, which is an international competition in a way to get people to Italy to do a week-long workshop. So there are many activities in education, and the reach goes much further than the tens or thousands. There's a multiplier effect, of course. Another thing that came up that's very valuable for some particular audiences is, of course, spin-offs. So we heard about a new masterclass, so this is for high school students, to learn about particle therapy. So we often quote particle beams in the use of treatments and particle detectors in the use of diagnosis in the medical world, and this really influences many people. In addition, there's witness stories, so stories about how society has benefited from various things that we do in particle physics. These are very powerful messages for certain audiences, and for nearly every audience, there's a reason to include these things. Other types of audience we reach include the arts world, or people who may not normally be interested in science. And you've seen some of that downstairs with the very nice exhibit on the ground floor here. One of the things that I think was key to this was inclusion of artistic projects, if you like, improves us to be able to think creatively and not just critically, which is very useful for our field, of course. And there are some very imaginative things used in if you call it arts, so from proton cookies that kids can make at science fairs to whole efforts to bring the arts and sciences together in schools and then have exhibitions at a national level, as in Italy with this with this project here. So the thing I really want to emphasize here is indeed that creative thinking is something we can all benefit from. Thinking out of the box definitely helps us with what we do. Continuing on the theme of science and arts, some of you saw the cosmic piano, so the scintillator-based music system that was demonstrated by our colleagues from Mexico. And this wasn't only demonstrated here, but there was a music festival, or we like to call it a science festival, featuring some music in Ostrava, so just 3 hours away from here at the weekend. So they presented the cosmic piano there, but in addition, at this same music festival, there was a presentation given by Fabiola and by Charlotte to about 300 people, a really packed audience. The most interesting thing for me was that the questions were excellent, really informed questions. There's a public there that's really engaged. They want to know more. And I really like this photograph here of Fabiola answering one of the questions using Charlotte's T-shirt and explaining a bit about the Lagrangian and so on. So it was a very entertaining way of showing people things. There's also books, and this is another artistic project where real scientists have teamed up with real authors to write fiction stories. The message there is really, don't be afraid to try something new. There are all sorts of ways to communicate. Don't be limited to just giving talks like I'm doing now. Another way that is becoming more and more popular is through games. And Atlas showed that they run games workshops for people to try and develop games themselves based on the Atlas detector and the physics that it's doing. There's also a board game that was shown that is produced in Czechia that includes the whole process, the whole scientific process, including funding and the publication of papers and so on. And it seems like it has an audience. People want to get in deep in this sort of thing. And then there's a collaboration between a French institute and a major software developer, Ubisoft, to develop a Mario-style platform game that you have to pay for, that features Feynman diagrams, Higgs physics, and so on. This is already proven to be very popular, and it hasn't even been released yet. People have signed up to get this game on their own systems. So these initiatives target audiences that may not look at science and hydrogen physics normally, and these are all brilliant things to do. There are other things that also target more a public audience, like exhibitions, and there was a quantum mechanics exhibition in Trento in Italy that focused on storytelling about things as deep as quantum paradoxes, a bit similar to what's in the Science Gateway, in fact. And again, the public's response has been phenomenal. There's been 100,000 visitors in the 6 months that it was going. Also in Italy, there's the Researchers' Night. This goes on all around Europe, in fact, but I wanted to highlight one thing that came out of the talk on the Researchers' Night, which was that guided tours of labs were really, really popular. Not just Frascati or CERN or DAISY, but the labs in the home institutes. And these involved postdocs and students who could then explain their science better because of this. The last thing I want to show in the parallel sessions really is visits and how we can improve inclusivity by allowing people to visit remotely through virtual reality. So you can visit the CMS detector remotely using just a headset. And this is also being used for engineering purposes, so not only outreach purposes. Atlas have a similar thing, but with a cheaper headset using this Google Cardboard. And then there are virtual visits run by nearly every experiment, so people can really connect to major facilities without having to travel. Social media. So this is a big thing, of course, and the way we use it needs to be figured out in detail. And DAISY, for example, use this to help with their recruitment, to show the daily lives of real physicists and engineers and technicians. And there were hints given by other organizations such as ALICE and CERN about how to do it better. So there are lots of benefits in education and outreach, benefits of getting involved in these activities that range from improving our creative thinking, better understanding of the big picture of why we're doing all of this. Very often we're very focused on the analysis we're doing or the detector we're building, but getting involved in education and outreach gives you a much wider appreciation of the whole hydrophysics landscape, and it helps us explain our physics more clearly. In fact, one of the talks was about how to talk to the public, and all of the guidelines given were completely applicable to giving a talk to our peers in hydrophysics. Final couple of minutes on the panel discussion. So we didn't know what to expect from this. We'd never done this before at an ICHEP or a major conference. We managed to assemble a group of 5 people, 2 of them professional communicators on television virtually every week, one from the BBC and one from Czechia. We had 2 esteemed physicists, Paris and Sarah, and then we had one who straddles the border between communications and physics, which is Matt Chalmers from CERN. So various reasons why we had this. I'll let you read through this in your own time. But the main thing we wanted to get across was this is something that everyone involved in HEP needs to do, to communicate what we do. As I say, we didn't really know what to expect. We were hoping for about 50 people in the audience. In the end, we got 150 people who stayed there for about an hour and a half. And it honestly could have gone on for another hour. There was lots of discussion, lots of questions from the audience. We really let the conversation flow in a natural direction. And there were lots of advice given by the panel members. And the feedback from the panel members themselves is that they also learned a lot from this. I have some quotes. I'll just read one of them, which I think is really powerful, which was from Matt, that the story of particle physics is the ultimate narrative, beginning and possible end of the universe, and lifts people outside their everyday lives. They're interested in what we do. We have to build on that. And indeed, there was the session yesterday about future facilities that indeed built on that. And Fabiola said that, the public are fascinated by our research. It's the modern equivalent of where are we going? So there's a big interest in the public that we need to jump on because people want to know about what we do. I bring back the bottom lines. Everyone should be doing something, in our opinion, towards education and outreach. And it's not just for the benefit of the outside world. but it benefits us as well as physicists and engineers. And these activities should definitely be supported, encouraged by the hierarchies. So I end with a picture of Connie and Mira, who have run away from doing this plenary talk. We need you to help pass the messages. Thank you.
Yeah. Thank you very much. And the talk is open for discussion. I see a raised hand over there.
I don't know how you can see the raised hands.
Hello. There's one thing I'm sort of missing in all these education outreach discussions. Everyone should be doing that, but what you're showing is sort of the tip of the iceberg, and there's a lot, tons of work behind this, organizational, technical. Let me give you an example, like master classes. I mean, I'd spent 2 hours of my time, but there are weeks of work to set it up, install the software, reserve the computer rooms, reserve the lecture halls, and so on and so on. There are students or us doing this. And you could go on with all the events. Somebody has to organize it. It takes a lot of time, and there are usually highly qualified people trained in top physics doing this. And the question is, isn't this waste of their time? Shouldn't they do something else instead of spending really days and weeks in organization? So where's the limit? Because I think this is why many people don't do it. Because it's not just, giving an interview and giving a public lecture. I mean, the work is this.
So you're right that some activities definitely take a lot of effort, and masterclasses is one of them. There are many, many other activities that don't take so much effort. Making a short video to go on YouTube or go on TikTok, if you like, is rather quick these days, and many young people are doing this. We did, for CMS, an event with the local community quite recently, and we didn't do much organization at all, and it was extremely well appreciated by the local community. It didn't take much work. So there is a wide range of, how much effort you really have to put into it. But the thing I really want to say is, I'll come back again to this. The things we do, I certainly believe, and I think a lot of people involved in education and outreach activities believe, is that it's beneficial for us. We get better as scientists by doing this, and the investment is worthwhile.
If I can, I'd like to disagree. If I can make a video very quickly and post it, and then nobody cares. I mean, 20 of my friends will like it, and then nobody cares. You have to build up your identity on social networks. Unless you are a CERN or somebody who is really well known, I mean, it again takes a lot of time to build up your
So what I meant there was you can make the video and go through the networks of CERN, of DAISY, of Fermilab, of KEK to publicize these things. You don't need to publicize it on your own one. But we'd like you to do it, and we'll get you to do a TikTok video after this meeting.
Okay, I think there's another question here.
I don't know. I have another question. Maybe this was discussed in the panel, I don't know. So I have seen lots of ideas in your slides, and I was wondering if there's a database of contacts which you could contact if you like this idea and would like to have more details about how this is prepared and what material you need, and et cetera, is there such an idea for a database, maybe?
So it's a very good question, and one that Yirji has been talking about with me and others, and Pedro, I see, is in the audience. There is a database of some things through the International Particle Physics Outreach Group, IPOG, that Pedro is going to put his hand up there, who leads.
Talk to me if you want to know more about IPOG.
Yeah. So, but what I will do is I will add a couple of slides at the end of this, put them online, and have the contact details for the different activities. We need a better database because there are so many good ideas coming out that we can all benefit from. and don't actually take too much effort to copy.
We have time for one last short question here.
Okay, I was going to actually bring up IPOG for this particular question. Also to answer the previous point of the amount of work it takes to do things and getting recognition. So there are people who are specifically spending their time to try to facilitate that, to make it easier to do masterclass. There's people dedicating resources in IPOG and other areas to make those work more easily for people who want to do the outreach. But I do think the last line up there is the most important, is that, you know, we do lots of things as physicists, which are services. We do shifts, we do things which you might say, oh, they aren't really necessary, or, you know, maybe we should be using our time in another way. But we always have to do service work, and this is a service work, and I completely agree with Dave's point there. This needs to be acknowledged, and we need to somehow convince our own colleagues, our senior colleagues, that when they are hiring people, that is something they should look for in a CV, as well as someone who can build hardware and write software and do analysis. It's very important that you hire someone who can do communication, education, and outreach.
Yeah, thank you very much. And I think on this note, we should stop because we are running out of time. So thanks again.
Thank you.
Okay, many thanks again. Okay, and next we'll continue on the theme of high energy QCD, experimental physics overview, and this will be given by Josu Cantero.
Thank you. Hi everybody, I'm going to present experimental results on high energy QCD physics on behalf of the Atlas, EMS, ALICE, and LCB collaborations. Before showing the results, let me briefly explain how a proton-proton collision is explained in terms of QCD. A proton-proton collision is a quite involved phenomena which requires several different QCD phenomenology aspects which enter in order to explain the collision. This phenomenology, in general, I mean, this depends strongly on the observable, but can be separated in terms of the energy scale, such as the High interaction. Here, highest energies are involved. Then we have the parton branching evolution. The typical energy scale goes between the higher interaction energies to lambda QCD, which is the scale which is associated to the hadronization, and the scales around, and then the hadronization effect, which happens with 4 scales similar to lambda QCD, which has values around 100 MeV. So we need an extra ingredient, which is called the parton distribution functions, which are used in order to convolute the partonic cross-section in order to get the cross-section in terms of the colliding initial state protons. In a proton-proton collision, so we have quarks and gluons within the proton that interact in order to produce the most energetic objects in the event. So the interaction between the quarks and gluons, which are within the same proton, can be ignored at this stage. And this cross-section can be described in terms of the perturbative QCD. So this is due to the fact that at high energies, we know that the value of the strong coupling constant, alpha S, takes small r small. So this, as I was saying, allows to perform a perturbative series on alpha S in order to describe the partonic cross-section. So for example, if we truncate the series at nestily in order, we know that due to this truncation, we are going to have theory uncertainties around 20%. If we go beyond nestily in order, the corresponding uncertainties will really reduce to factors to 5%. Let's say that we have produced 2 high PT quarks in the hadronic in the parton interaction. So these quarks are going to start the QCD radiation, so are going to radiate gluons. These gluons will radiate more gluons, and at the end, this will produce a QCD cascade. Here, this diagram shows you how these emission angles decrease as the final state quark is produced. So at the end, such as at the end, we will have a bunch of collimated particles that we call jets, that are represented here with these gray areas. So this is a multi-scale process that is proving all order of the perturbation theory. So we also know that if we go towards lower energies, the value of alpha is increased. So basically, we need to perform a resummation of different orders in order to have a fair description of the QCD shower. Finally, once the finalized state parton has energies close to lambda QCD, they will recombine to form colorless particles that we call hadrons. And these hadrons are the particles that will interact with our detectors. So all of these phenomena can be explained by the QCD Lagrangian, which has 7 free parameters that need to be determined experimentally. 6 of these are the quark masses, which have an electrowave origin. And then we have only one parameter, which is the strong coupling constant, which is the only fundamental parameter of QCD. So this means that QCD is a quite predictive theory. It has also the asymptotic freedom property, which basically means that the alpha S decreases towards we go to higher energy scales, in contrast to, for example, with the QD coupling constant, which increases toward high energies due to the screening effects. The alpha S is the standard model coupling constant with the largest value, so this means that the QCD corrections are, in general, quite important for most of the processes that are measured in the LHC. So this also means that we need to have a good understanding of these QCD corrections in order to try to perform thorough tests of our standard model theory. It also affects the vacuum stability due to the dependence of the Higgs coupling on alpha S through the renormalization group equations. You can see here how this lambda coupling evolves with the energy and the dependence with different alpha S values. So due to this, it is very important to start alpha S with high accuracy. Okay, now I'm going to talk about these measurements are useful to tune these long-distance effects, such as hadronization. Hadronization plays an important role in order to describe the jets from experimental point of view, since these particles after hadronization that interacts with our detectors. So in the case of the Atlas calorimeter, we know that the energy response is different for baryons compared to the pi zeros, which rapidly decays to 2 photons that are detected by our electromagnetic calorimeter. Here on the left, you can see the jet response as a function of the baryon energy fraction, and you see that decreases as this energy fraction increases. And on the right, you can see the prediction of this baryon energy fraction for the different Monte Carlo models as a function of the PT of the jet. And you see that there are large differences, and since we use these Monte Carlo models in order to basically correct this detector level energy measurement to the jet to make the final energy at particle level measurement, this will lead to uncertainties to our jet energy scale calibrations. It is also important to tune this Monte Carlo model in order to reduce the non-perturbative corrections that are typically applied to the theoretical calculations in order to have fair comparison between the theory and the measurements. So here I showed the jet energy scale uncertainty, some function of the PT of the jet in case of Atlas. So based on these studies, so the method in order to estimate this uncertainty was revisited. In particular, models that are disfavored by the data were not included. So this allows to improve in the low medium PT region the uncertainty. You can see here this if you compare the green area with respect to the black area. So we have also updated single particle deconvolution uncertainty. So this leads to improvement, especially here in the high PT region. And at the end, by including all this improvement, Atlas has less than 1% uncertainty on the generative scale for PTs of the jets above 70 GeV, which is quite impressive. This is one example of a measurement that can be used in order to tune our Monte Carlo models. This is a measurement by LHCb of the fragmentation function as a function of the energy fraction taken by the particles separated for different particles, in this case pions, kaons, and protons. The measurements were compared to the Lund hadronization model, which is included in the PICE Monte Carlo simulation, and you see that the Monte Carlo underestimates the measurements in the high C regions in the case of pions, whereas overestimates the measurements in case of kaons and protons. Moving on now to measurements which are suitable in order to test the different QCD resumation approaches, such as the jet substructure measurements. So these recent years, this is one observable that has been used quite heavily these recent years in order to test or to prove different QCD resumation approaches. This is the Lungen plane, which is a theoretical representation of the phase space with the jets. This includes the information of the QCD radiation history. And how we get the information of this QCD emission? So this is done by applying the jet declustering procedure. Basically, we run backwards the jet clustering algorithm in order to get access to this pair of proto-jets that are reconstructed in the intermediate stage of the jet recombination. And we use the information of these proto-jets as a proxy of the QCD emissions to fill this 2D plane, and finally to get the Lungen plane, which is shown here. One interesting feature of the Lungen plane is that the different effects of the QCD can approximately factorize. For example, in the soft collinear regions, we expect to be more sensitive to hadronization effects, whereas in the wide angle hard regions, to be more sensitive to perturbative QCD effects. Alice CMS Atlas has released measurements of the Lungen plane, and recently Atlas has released measurements of the Lungen plane for boosted hadronically decaying W and top jets. Okay, here I want to highlight the CMS measurements on the Lungen plane that you can see here on the left, and on the right a comparison of the measurement for one particular delta R slice with the state-of-the-art theoretical calculation. The first observation that you can see is that the number of emissions increases towards we go to small KT values, and this is due to the alpha S running. So we expect that lower energy scales, the value of the Stochastic constant is larger, so this enhances the number of emissions. There is an adequate description of the measurements by the theory, as you can see here. However, these calculations suffer for having large uncertainties in the low KT region, and this is due to the non-perturbative corrections that are applied and are estimated using the Monte Carlo models. Okay, another set of observables that are quite suitable in order to study the internal structure of the jet are the energy correlators. So these observables are sensitive to the energy flow within the jet, and they have quite nice theoretical properties like symmetry and factorization. So here the idea is to see the jet constituents as a system of interactive particles that has evolved, and this evolution is driven by the QCD interaction. So by measuring, for example, the correlation between the two particles and also between the three particles, we can get insights of the underlying theory, which is QCD. In addition, we can go further and perform ratios of these three particle to two particles correlators in order to benefit for cancellation of the theoretical and correlated experimental uncertainties. Another nice feature of this ratio is precisely this observable depends on the alpha S value. And this dependence comes into the slope. So for example, if we increase or reduce the value of alpha S, the slope of this distribution changes. And this was used by CMS in order to extract alpha S by measuring the slope of this distribution in different PT beams. So this is on the bottom, you can see the resulting distribution. And this distribution was used, as I was saying, to extract alpha S value that you can see here at mass of the C boson. This is the first measurement of extraction of alpha S using a substructure variable, which is also quite impressive. Alice has also performed measurement of the energy correlators, as you can see here. Another nice measurement of this distribution is that we can clearly disentangle the regions which is basically driven by perturbative QCD. So here we see the behavior expected from a system with interactive particles. Then we have this region, which is the confinement region, is when the partons transform into hadrons, and then a region which is basically dominated by the hadronization, and it is compatible to assuming that the hadrons are free. Basically, this means that at these scales on the angular separation between the particles, the energy distribute uniformly. Alice has also performed measurement of the correlation between the three particles over two particles, and these are compared to the with the state-of-the-art calculation, and you can see here that there is a growth agreement between both. Moving on to experimental measurement that is suitable in order to test the hard QCD physics. Measurements with high PT jets allow to test perturbative QCD, stacked alpha S, and also the corresponding running. In principle, this depends on the value of the PT of the jets, but in principle are high energy scales. They have typically lower uncertainties compared to the low PT jets, and they are useful to extract the value of the PT jets, especially in this high X region. So this X means the energy fraction that is taken by the initial state parton with respect to the proton. One set of variables which are quite suitable in order to extract alpha S are the 3-jet to 2-jet ratio. So in this ratio, we can cancel, reduce the PDF effects, and we also can cancel out the correlated systematic and theoretical uncertainty. One of these observables is the delta R. So here you can see the CMS measurements of this observable as a function of the PT of the jet. The measurements were compared with the next to leading order theoretical calculation. You can see here that there is a good agreement of the data, and this was used in order to extract alpha S at the mass of the C boson. And here you can see the extracted value together with the total uncertainty. The total uncertainty is dominated by the uncertainty on the next to leading order calculation, which amounts 10%. The running was also extracted, which is shown here for energy scales between 400 and 2 GeV and 2 TeV, and you can see that the QCD describes quite well the measure running. Another similar observable, in this case, energy-energy correlations are measured in 3-jet events between the jets, and then this measurement is normalized to the inclusive dijet cross-section. So this was done by Atlas. In this case, the measurements were compared to the next to leading and next to leading order calculation. As you can see here, when we go include beyond NLO terms in the calculation, we can describe the data very well. As you see, if you compare the black markers with the red lines. In addition, we can highly reduce the corresponding theoretical uncertainties. And if you can see this, if you compare this red band with respect to the blue band, which is the uncertainties corresponding to the next to leading order. This distribution was used by Atlas in order to extract alpha S, and you can see here the corresponding value. And you see that by using the next to leading order theory, we can reduce highly the corresponding theoretical uncertainty contribution to, in this case, 2%. The running of alpha S was also measured by Atlas and compared with these NNLO calculations, and you can see here that the calculation describes quite well the data. In general, we can perform 3-jet to 2 ratio measurements as a function of the several variables. So as you can see here, in this measurement done by Atlas, here you can see all the observables. I want to highlight just 2, the ST2, which is basically the scalar PT sum between the leading and sub-leading jet, and this distribution, which is the delta Y max. So this is basically the largest difference in the rapidity between the 2 final state jets. Measurements as a function of this variable is quite suitable in order to prove topologies where we have well-separated jets. And this is precisely the topologies that we expect for this vector boson fusion and vector boson scattering. So you can see here the leading order feedback diagram, which basically describes the vector boson scattering process. And in this case, these 2 quarks are going to produce in the final state 2 well-separated jets. This kind of final state suffers from the so-called multi-scale problem. Basically, this means that we have 2 scales with different values. In this case, these 2 scales are going to be the PT of the jet, and the other one, which will have largest values, is the variance mass between these 2 jets because they are well-separated. So in order to have a fair description of this kind of topology, we need to perform resummation of this kind of logarithms, which typically have large values. This is done by high-energy jets collaborators, and the prediction were compared this time with the Atlas measurements of these R32 as a function of this delta Y max. And you can see that measurements are adequately described by the calculation, but there are still some differences which point in the direction that this resummation needs to be tuned to improve the agreement. On the bottom left, you can see the systematic uncertainties of the R32 as a function of ST2. This measurement includes the precision recommendation that I was talking about at the beginning of the presentation. As you see, that in this case, we achieve uncertainties which are well below 1% for a large range of ST2, which is quite amazing. And on the middle and on the right, you can see the corresponding measurements compared to the NLO and NLO calculations for different tightness of the PT of the third jet. And in both cases, you see that by including beyond NLO terms, we improve the description of the data, which reduces theoretical uncertainties. We can also use dijet production events in order to test the QCD dynamics. So the IHEP events allow to perform thorough test of the perturbed QCD, because basically having 2 jets allow us to measure double or triple differential cross-section, and in particular in phase space region, where we can clearly separate between different topologies, as you can see in this plot. Here on the left, you can see the measurements compared to the NLEO calculations. You see that in general there is a good agreement of the measurement. And since we in contrast with the ratio, in these measurements, we have a sensitivity to the PDF, so we cannot extract directly, let's say alpha S, but we need to perform combined PDF plus alpha S fits. This was done by CMS, and this is the amazing extracted value. And now, with a 1% theoretical uncertainty, thanks to including this beyond NLEO terms to the calculation. And here on the bottom, you can see the impact of including these measurements to the HERA data, and you see that the uncertainty on the gluon PDF, especially a high X value, can be reduced. This is the last analysis that I want to highlight before the conclusion, which is the measurement of the PT of the C boson in the inclusive C boson production. So this distribution, this observable, is sensitive to alpha S, basically due to the initial state radiation, which is recoiling with the PT of the C boson. And you can see here how this distribution changes if we increase or reduce the alpha S value. So this was used by alpha S in order to extract this was done by Atlas in order to extract the value of alpha S. You can see here the corresponding extracted value. You see that these calculations are quite precise. So this is N cubed to NLEO calculations. There is another interesting feature from an experimental point of view, which means that in this kind of final state, we don't have jets. Basically, we have 2 leptons which can be measured experimentally with high accuracy. So this, in general, reduce the experimental uncertainties on the alpha S extraction. And you can see here the extracted value. As I was saying, this is the most precise alpha S extraction using one unique measurement, and the uncertainty is comparable to the wall average, as you can see here on the bottom of the middle plot. Okay, this brings me to the conclusion. I hope that I have convinced you that the QCD has a quite rich phenomenology. There has been, and there are currently, huge efforts from the experimental and theoretical side in order to reduce the experimental systematic uncertainties and also theory uncertainties. So this allowed to perform quite thorough tests on the QCD in a wide range of energy scales. And here I just to show you another interesting results that were not covered in this talk, in case you are interested. Many thanks.
Okay, many thanks indeed. We're open to questions. Maybe I can start us off while we're waiting. I wonder if you could say a little bit about what you might expect in the high luminosity LHC era. Now, clearly, we'll have significantly more powerful detectors with extra capabilities, but we'll also have higher pileup as well. What are you looking forward to for the next years?
Well, with more data, we can increase the statistical precision on the running in these regions. So we know that, for example, if there are beyond a standard model particle which has color, this will affect the running. I mean, if the mass of these particles is large enough, this will affect the running. So we can test, indeed, beyond a standard model theories just by measuring the running at this stage. So having improved detectors, we can further reduce the systematic uncertainties on the jet energy scale values. So this has been a quite huge achievement. So to have less than 1% uncertainties on the jet energy scale. Yeah, in general, I think from the experimental point of view and also from the theoretical point of view, this can be quite useful. Yeah.
Many thanks. Are there any further questions for Josu?
Yeah.
What about that? Okay, perfect, thanks.
Yeah, okay. You show many different results of alpha S extraction. Is here. And okay, very last one are more or less all compatible among each other. Point to alpha is 0117, 0118. But the very first one you show on the ratio correlators point to a 0122. I mean, yes, this was much higher. So I want that you comment on this. I mean, why here the alpha S that come out is much higher than in the other case?
Well, I think in both cases, if you take into account the uncertainties, they agree within the uncertainties. So if you sum of these uncertainties, this alpha S value, I think, has around a 5% uncertainty, which will cover the whole average, and also the alpha S atlas measurement. I mean, this is a quite new measurement, and what I see here is that since this is the first measurement of the jet type structure, and as I was trying to explain before, this QCD cascade implies a huge range of the energy scales. So with a better theoretical calculation, I think we could extract the alpha S running to lower energy scales. So in principle, I mean, if you see here, okay. Most of the Atlas and CMS running extraction are beyond 100 GeV. So by using these observables based on jet substructure, we could get access to the alpha S running to energy scales around here, which is quite nice. Yeah.
Okay, many thanks. We have time for maybe one more question. Okay, perfect.
Yeah, thanks for your presentation. I'm wondering, you discussed effects where you have a hard process at the beginning and then eventually soft process, non-perturbative. And I wonder whether you could comment on effects which are intrinsically non-perturbative, so not just factorization of perturbative and non-perturbative. So
like which one?
Like hardcore, hard diffraction.
But you're talking about from a theoretical point of view or experimental?
Either.
I mean, the next talk is about theoretical developments on QCD, so I think it's
thank you.
Thank you.
Okay, many thanks, and let's thank Josu again for his presentation.
Thank you.
And so now let's turn to the theory part, and Kirill Melnikov is going to tell us about QCD calculations, perturbative, and so on.
Okay, hello. I hope you can hear me. So let me start by thanking the organizers for the opportunity to speak here. In my talk, I would like to summarize status of perturbative QCD calculations, focusing mainly on the LHC physics. I would like to talk about open problems in the field, and then talk a little bit about future research directions. So one of the main goals of the physics problem at the LHC, of the physics program at the LHC, is to study hard collisions between protons, collisions where protons exchange very large momenta and basically disintegrate. Such events are interesting for two reasons. On the one hand, when they occur, there is so much energy that is packed in a tiny space-time volume that heavy standard model particles, and probably even particles that we still would like to discover, can be produced. On the other hand, thanks to the phenomenon of asymptotic freedom in QCD, such events can be described in terms of quark and gluon degrees of freedom with great confidence and also with great precision. This, in spite of the fact that such events occur in the collisions of hadrons and are observed in multi-hadron final states. Now, perturbative QCD is by now an extremely well understood theory. For this reason, its goal in connection with the LHC physics is to facilitate comprehensive studies of standard model physics and hopefully help with the discovery of physics beyond it. This is an extremely important role because in the absence of advanced QCD calculations, we will still be completely in the dark about proper interpretation of basically all the measurements of hard processes that have been done at the LHC. A case in point is the Higgs production in gluon fusion, where theoretical predictions change by about a factor of 2 when you go from leading order predictions in perturbative QCD to the highest order that is available right now. You can also see an excellent agreement between different theoretical predictions and corresponding experimental results in the left pane of this slide. And this basically tells us that the theoretical modeling of hard hadron collision is truly extraordinary by now. Demands of the LHC physics program have shaped the development of perturbative QCD and actually kept practitioners of perturbative QCD on their toes for a very long time. You can see this by comparing the two so-called wish lists, which enthusiasts of perturbative QCD from both experimental and theoretical communities put together every 2 years. If 20 years ago, next to leading order QCD calculations were considered to be necessary, current wish list includes sort of requirements that certain processes are to be calculated to third and even fourth order in the perturbative expansion in QCD. Calculations in such high orders for a theory as complex as quantum chromodynamics and for a variety of processes that you see in this list, they're simply impossible if we use traditional methods of perturbative calculations that Feynman, Hooft, and Weltman taught us. So basically, one of the major avenues along which the development of perturbative QCD progressed in the past years was a development of new and sometimes radically new ways of performing perturbative calculations that actually make calculation of this complexity possible. Evolution of perturbative QCD was very impressive in the past, I don't know, 10 years. But we should not forget that, after all, we want to describe processes that start and end with hadrons. For this reason, if we want to improve theoretical description of such processes, we need to address two challenges. One challenge is probably technical. So we need to keep developing efficient methods to describe quark and gluon collisions, going to higher and higher orders in perturbative QCD. This is a multifaceted problem. I'll talk about it in the second part of the talk to some extent, but this is a problem which is well understood. I believe that there is also another problem, which I think is of a more conceptual nature, because this reflects the fact that we look at the collision of hadrons and observe what is happening also by looking at hadrons. So we basically need to find a systematically improvable description of these transitions from hadrons to protons and back. And I think this problem can only be addressed if a better understanding of non-perturbative QCD effects in collider processes is achieved. We don't talk much about this problem, but I think it slowly becomes relevant, especially because of the appearance of what I would call ultra-high precision measurements that are performed at the hadron colliders, not only at hadron colliders, but these are basically measurements of the top quark mass and the strong coupling constant. And I think absence of this very clear understanding of non-perturbative effects causes enormous confusion in the interpretation of these very high precision results. So in what follows, I'll talk about these two challenges and in turn, and I'll start with the perturbative one. So if you want to perform any perturbative computation in QCD, you basically need to do several things. They're well defined. You need to calculate loop amplitudes, and of the type you see here, and you have to also calculate real emission contributions of the type that you see here. Taken separately, these contributions are poorly defined. They exhibit so-called infrared divergences, and only if you put them together, you actually get something that you can compare with the experiment. So to perform phenomenologically relevant computation, I need to do three things. I need to find a way to compute these virtual loop amplitudes. I need to understand how to do a calculation of this type. Then I need to understand how to integrate the infrared divergent contributions over partonic phase spaces, so I have to deal with these kind of things. And then I have to, once I found a way to do this, I have to implement the imagined procedure into a numerical code, because I need to turn formulas into numbers. Now, let's talk a little bit about the problem of loop calculations. Now, this problem is peculiar, because this is basically the problem of calculating divergent integrals of rational functions of the type that you see here in Minkowski space. Now, stated in this way, this problem sounds relatively simple. After all, we start learning how to do integrations in high school. But this problem turned out to be very difficult to tackle. And until now, we don't have a satisfactory general solution. On the other hand, it is to be said that many ideas and attempts to solve this problem produced a large number of interesting theoretical methods that over time became part of the theoretical toolbox that we routinely use. I think a very important part in these attempts to address this problem is occupied by numerical methods, where the idea is to construct a robust numerical framework for doing loop integrations, and there are plenty of different ideas out there how to do these integrals, ranging from direct integration over loop momenta to integration over so-called Feynman parameters, all of this after you subtract some singular contributions that prevent you from sort of direct calculation of these integrals numerically, and all the way down to trying to solve differential equations numerically that these integrals satisfy. So I think that as we move forward, given the complexity of the processes that we want to address with this type of calculations, the importance of the numerical methods will probably keep increasing. But I also think that even now we don't have a clear idea of how the ultimate solution to this loop integration problem will look like. This is a rapidly changing field. There is a place for new ideas. There is still a lot of things to do. Now, on the other side of the spectrum, we have the real emission contributions, and they have to be integrated over the phase space, and this is usually done using the so-called subtraction or slicing methods. In both cases, as the name suggests, you either subtract away the singular contribution of the integral that you would like to calculate, or you slice it away by putting some constraints on the phase space. Now, these things that are subtracted away or sliced away, they need to be integrated separately. They typically don't depend in a non-trivial way on the kinematics, and you can integrate them independent of the constraints on the phase space that you put to perform realistic calculation, to describe realistic experimental situation. So integrals of these quantities then produce infrared and collinear divergences that when you put together these contributions with virtual corrections cancel and give you a well-defined remainders. So in spite of the fact that a very large number of next to lead order calculations for very different processes has been performed, this sort of cancellation between infrared contributions induced by infrared, by real emission parts of the calculation and by virtual loops was always always proven on a case-by-case basis. Now, in recent years, extensions of existing next to lead order slicing and subtraction scheme appeared, where such cancellations of infrared problematic pieces were demonstrated analytically for completely arbitrary processes at colliders. And I think these developments basically bring us one step closer to the formulation of a subtraction scheme at next to lead order, which will be easily amenable to the automation. And hopefully it will enable us to construct sort of some general purpose codes of the type mud graph at next to lead order. It will become mud graph at next to lead order that once and for all will solve the problem of real emission contributions to arbitrary processes at next to lead order in QCD. So this is something that one can hope for. Now, I think I want to summarize this part, the part about sort of perturbative challenge. I want to say that we currently do have a highly developed theory of protonic collisions that can be used to describe very complicated collider processes. There is not much to say about leading and next to leading order calculations. The only thing I want to mention in the context of next to leading order calculations is that at that order we now have a wonderful treatment and complete treatment of intermediate unstable particle. At next to leading order, we keep computing more and more things, but the limiting factors currently are the availability of virtual loop amplitudes. As I said, we don't know how to solve this problem in general, and then the efficiency of implementation of subtraction schemes in numerical codes. I'll show you an example of this later. Now, I didn't say anything about next to leading order calculations. This is sort of a new frontier. We do have results for 2-to-1 processes, Higgs production, W production, Z production, some basic kinematic distributions, rapidity distributions, for example. And in principle, we have a slicing scheme that will allow us to calculate the production of an arbitrary colorless final state in proton collisions, but the amplitudes in this case, virtual amplitudes, are not available. Okay. So I want to, before I go to this the discussion of this conceptual problem, I want to say a few words about or illustrate how this technical problem, progress that I discussed now, leads to sort of a better phenomenological predictions. And I'll have several examples. They're selected because of my personal interests. Now, the first example that I want to show is something that LHC is a unique thing that LHC experiments can do. Namely, they can study the running of the strong coupling constant at very high energies. Now, a useful observable to extract the strong coupling constant are some type of shape variables, and you should look at the places which are sort of saturated or not saturated, where this widget contribution is the leading one. Next to leading order predictions for the shape variables in hadron collisions were known since quite some time, and recently the next to leading order predictions for widget production at the LHC have been calculated, and this is tremendous achievement. Now, this result is based on a very complicated two-loop amplitude, which was possible to calculate using this very advanced modern theoretical methods that I briefly mentioned in the previous part of my talk, and an extremely robust subtraction scheme that is capable of dealing with processes of this complexity. Now, Atlas collaboration performed the measurement of the strong coupling constant looking at a particular type of shape variables, and this is the result that you see. These are experimental points, and they're compared to the prediction and of alpha S extracted. This is how alpha S ran it, around 1, 2, 3, 4 TeV. And this is the result for alpha S if you extrapolate these experimental points down to the mass of the Z. So you see that this is an excellent confirmation of the fact that we do understand the running of the coupling constant. And the virtue of having this next to leading order predictions is that they allow you to reduce the error on the extracted value of alpha S by about a factor of 3. Now, the other interesting aspect of this calculation is that it is extremely computationally expensive, as you see here. You see the computational cost. And this basically tells us that if we hope to construct a sort of a framework for next to linear QCD calculations that will enable us to calculate, to make predictions for processes of even high multiplicity, then in one way or the other, the efficiency of these calculations has to improve. My next example concerns the determination of the Higgs widths from the off-shell and from the comparison of off-shell and on-shell production of 4 leptons. The interpretation of this measurement in terms of the Higgs widths relies on theoretical predictions for the irreducible background, that is glue to Z in this case, where Z is coupled directly to Borg loops, as what you see here. Now, when the first extractions of the widths happened, the calculation of this background was performed to next to leading order in perturbative QCD, but only for massless quarks that propagates in this loop, because the contribution of the top quark loop to glue to ZZ was too complicated to handle. And so only some approximate a way of dealing with, of accommodating the top loop into glue to ZZ amplitude was developed. At that point, it was believed that this is a good approximation, but of course it was very clear that a confirmation of this approximation would be highly desirable. Now, this happened as of earlier this year, where this gentleman that you see here, they actually calculated the top loop contribution to GLU 2ZZ and using some very sophisticated blend of numerical analytic methods. And what happened is that they actually confirmed the approximation that was used in the previous calculation. So this, I think, puts the extraction of the Higgs weights from the on-shell and off-shell comparison on a very solid footing. My next, the next thing I want to discuss is again the extraction of alpha S, but now at low transverse momenta. It's not easy to come up with an observable that will allow you to measure alpha S at the LEC with a precision that is competitive to the world average. But these gentlemen managed to sort of realize that Z transverse momentum distribution is the place to look at. Atlas collaboration performed the measurement and got this result. It is extremely well compatible with the world average and has a very small uncertainty. Now, I think I want to sort of emphasize that a percent level prediction for Z transverse momentum distribution requires us to employ some of the most sophisticated calculations on perturbative QCD ever performed. You see the list here. This list of different things goes into prediction of this transverse momentum distribution. And I want to say that this is not something that one person can do. This is actually a list of people who, in one way or the other, over many years, contributed to making this theoretical prediction possible. I also want to emphasize that, this is also a very clear example or illustration of the fact that that without this theoretical methodological developments that I discussed at the beginning of this talk, this kind of calculations, predictions for this observable would not be possible, because these calculations would definitely not have happened without new ideas and new theoretical methods. Now, my last example concerns the determination of the W mass and mixed QCD electric corrections. You see the example here. These corrections are extremely tiny, but they're different for the Z boson and the W boson. And since Z samples are used to calibrate W samples, these corrections actually may become relevant for the determination of the W mass at the current level of precision. So I'm not an experimentalist. I don't have an access to the full analysis chain. So I do a simple estimate where I calculate the first moment of the lepton transverse momentum in Z case and the W case, and I compare how well they're correlated to the respective masses. So because these corrections are different, there is a slight misalignment of this correlation. And if I account for these corrections, then basically I find shifts in the W mass at the level of a few MeV. What is interesting is that these shifts, they seem to be very strongly dependent on the exact selection criteria that one applies to identify leptons in Z and W events, and typically these selection criteria are slightly different. I'm pretty sure that these shifts will not survive the full experimental simulation toolchain, but I think it's an interesting illustration of how a very complicated calculation of the type that you see here and a very complicated experimental analysis can work together to produce interesting results of a direct phenomenological relevance. Okay. So let me just very briefly talk about this issue with the non-perturbative power corrections that are referred to as conceptual problems in the beginning of this talk. This is a conceptual problem because we have no idea how to solve it. Typically, we estimate these non-perturbative power corrections, these hadronization corrections using hadronization model and parton showers, but for very high precision observables, this is definitely not sufficient. So I think you may be wondering why I talk about these non-perturbative effects in a talk that is centered around perturbative physics. And I think that I do this because thinking about these non-perturbative effects and understanding them from first principles turned out to be very difficult. And so it is basically not possible at this point to do this, but there is this whole idea that if you look carefully at perturbative calculations, maybe you can say something interesting and halfway profound about non-perturbative ones. Now you can see something like this happening in the discussion of an interdependencies between perturbative evolution of parton showers and hadronization models due to the infrared cutoff and parton showers that these people put forward. We can also think about it in the way that when you do Feynman integrations, you have to integrate over all momenta, including the soft ones, and so you can at least use Feynman diagrams to estimate the sensitivity of what you're trying to calculate to the problematic integration regions, which are basically soft momenta regions. One can understand the famous Kinoshita-Lee-Nauenberg infrared cancellation in this way, as well as the whole idea of renormalons and the relation to a QCD with a fake gluon mass. You can always understand it in this way. Now, the idea to use infrared renormalons to say something about non-perturbative effects at colliders is not a new idea, but it got recently resurrected in the context of LHC physics, because it was realized that one can calculate this leading power corrections to very complicated processes using the so-called low Burnett-Kroll next to soft emission theorems and a few tricks from the perturbative toolbox. The approach based on infrared renormalons is not perfect for estimating non-perturbative power corrections. It has significant limitations, but it can also lead to an interesting physics insight. So you see them listed here. So for example, you cannot determine the pole mass of the top quark from top production cross-section with a precision better than 300 MeV, okay? So this is something that experimentalists call indirect determination of the top quark pole mass. It's not possible with the precision better than this. If you look at even basic kinematic distributions in top quark production processes, you will find that there are linear power corrections that are not part of the Monte Carlo. At least I cannot imagine how they can be. Then if you look, for example, at electron-positron collisions, you find that non-perturbative corrections to shape variables in 3-jet and 2-jet regions are actually different in spite of the standard assumption that is being used when the alpha S is extracted from shape variables at lab. And so I think there are plenty of interesting physics related to this, especially in connection with these ultra-precise measurements that include the top quark mass and the alpha S. But of course, I'm running out of time, so I cannot discuss them. And so if you want, you can ask me in the QA session. And so this takes me to my conclusions. And I'm not going to read this. I'll just say that perturbative QCD, as far as we're concerned, is an excellent shape. There is still a lot of things to be developed. But I think this impressive success has also put a lot of pressure on understanding the non-perturbative power corrections at hadron colliders. Because without such an understanding, further improvements in ultra-precise determination of physical parameters, such as the top quark mass or alpha S, for example, may not be possible in spite of being statistically accessible. So thank you very much for your attention. That's all I want to say.
Okay, is there an urgent and short question there?
Kirill, thank you for a very good talk. In the beginning, you had the scaling of Q of about 30, it's over here, 30 GeV, and lambda QCD is 0.3. So are you hinting that the non-perturbative effects are really at a 1% level for various observables like this? I mean, you talked about the top quark mass, of course, but I'm saying because the kind of general naive, non-expert view is that things go like lambda QCD squared over Q squared, and that's, of course, extremely small for the LHC. But
lambda QCD over what? Sorry?
Lambda QCD over Q, or everything is squared, so it's a very tiny effect.
No, that's exactly what I'm saying. So this is a very naive understanding. They don't go like lambda squared over something squared. They go like lambda. So in the case of the top quark, the correction is lambda to the mass. Okay, so it's not 30 GeV, it's lambda. Okay. Lambda over m, if you wish. So, of course, if it were a lambda or something squared, this will be completely irrelevant for the LHC. Right. But there are linear effects, we know that they exist, and they typically exist for many observables. This is the point.
Right, but you chose Q at the beginning, you showed like 30 GeV as a kind of
this
scale.
is a typical cut on the transverse momentum of a jet that you might be looking at, right?
Okay, thanks.
Okay, unfortunately, we have to cut this short here because we are running out of time. Thanks very much again, Kirill.
In the last few years, we've had an absolute wealth of new hadronic states being discovered. Indeed, I think next year will be the 10th anniversary of the pentaquark, and Xiao-Rui is going to talk us through some of these states that have been discovered in recent times.
Okay, thank you. First, thank the organizers for the opportunity to present this talk. So I would introduce you the recent progress within the recent 2 years about the hadron physics, but mainly experimental because limited by my personal expertise. So I divided my talk in roughly in 3 sectors, light hadrons and also heavy meson and heavy barons. So I cannot cover all the progress, as Chris just mentioned, a lot of results. So I just propose you to look for more results in the following nice parallel contributions in this conference. We know hadrons and the gluons are confined in the gluons, quarks and gluons are confined in the hadrons and with the scale of 1 femtometer, which roughly correspond to the non-perturbable QCD probe region. So study the hadron spectroscopy would provide the opportunity to study QCD just in a non-perturbable way. And in particular, the complex electronic exotic hadrons can reveal some new or hidden aspects or dynamics of strong interaction, for example, some symmetry and so on. So you know around us, more than 99% of the massive matter are actually contributed from the QCD potential. Besides the well-explored conventional 2-quark meson and 3-quark baryon, so we are very curious to learn about the other forms of the hadrons, which are already being allowed or predicted in different QCD phenomenological models. They are, for example, the tetraquark, pentaquark, and also some molecule states, and even QQ bar gluon hybrid or gluon bound state, purely gluon bound state, like we say global. Okay, there are actually a lot of experiments from the worldwide, and we know the ongoing machine like the BAS3 experiment, and also the BIO2 and RCB, Atlas CMS, and so on. They are providing different information on hadrospectroscopy, and also the fixed target environment like Compass GlueX. They are also working hard on that. So these 3 charts show you the recent progress, actually very nicely summarize all the progresses. And so my talk would cover only like the recent 2 years from the last ICHEP conference, and we see from RC experiments, BAS3 and also BIO, it's really quite abundant of the results. So for the light hadron sector, we see that from different experiments, they could study this through the very high statics of the GSI D or B hadrons, and also and different ways. But the awkward thing is that for different amplitude of the quark gluon operator, they could interfere with each other, and also they behave quite similar in the quite limited energy region, mostly from 1 GeV to 2.5 GeV. So it's make this light hadron spectroscopy very challenging to understand many of the properties. However, we always try to accumulate more data. So here I will show you one of the important progress from BAS3, that the X2370, which was firstly seen in GPSI reduced decay to pi E prime. That's quite some time ago. And however, after we accumulate 10 billion GSI events, we study this GPSI reduced decay, which is regarded as a gluon-rich process to search for global states. It's kind of like golden channel. So we implement the partial analysis with the GPSI reduced to K short eta prime, and we confirm this X2370 In addition, we also measure determine its spin parity to 0 minus plus, and also analyzing its decay rate and also the mass and the weight. We think about that it could be candidate with the latest pseudo-scalar global candidate, which is predicted by lattice QCD. And also we investigate more decay modes of the this 2370, and more than roughly like 7 decay modes are observed, which looks quite close to the behavior of the eta C decays. And we could think about it could like consistent with pseudo-scalar global. Other striking results actually was reported some time ago that BAS3 see eta 1 1855 with the exotic quantum number. This is 1 minus plus, which cannot be informed of the 2 quark meson. It has to be exotic state, which been widely discussed in theory, could be hybrid molecule or the other tetraquark candidate. And also the BAS3 use the high static threshold production of DS to identify a new A0 IOCB triplet. And also the BAS3 take a lot of high statics energy scan data. One example is that last year BAS3 see an enhancement around the lambda bar mass threshold, and in the eta in the eta pi lambda bar final states, and this feed shows that this X2356, which never been predicted in theory models. So it could be hexaquark or baronium, which we have not yet clue yet. And also another thing that last year we did a very comprehensive partial wave analysis of this ISO spin violating process GSI to phi eta pi 0, and show that in the phi eta final states we could see 2 new states, which very probably it's kind of like a new strontium states. So talking about the strontium states, let me try to recall that actually BAS3 actually did a very comprehensive study on the previously discarded Y2175, which BAS3 studied more than 10 different decay channels and find this Y states and which will be important to understand its nature, is whether it's just SS bar or it's other exotic hadron. And talking about the high static GSI events, from the GSI reduced to eta prime pi pi, you see that from 0.2 billion to 1.1 billion to 10 billion, the BAS3 see this eta prime pi pi mass spectrum in a much finer or more clear way to see that it's a fine structure and also more resonance structure there. And especially in the eta prime, in this PP bar mass threshold, you see a distorted line shape, which could be connected to the XPP bar in the GSI related to PP bar decays. And also for this GSI to related to 6 pions, you also see this distorted line shape at the PP bar mass threshold. In addition to that, in the bion sector, we use the high statics lambda C decays. For example, the bio, they see this lambda pi line shape could enhancement around the MK bar mass threshold, and also they also see this PK mass spectrum. There is also distorted line shape around the lambda eta threshold, and they conclude that it's due to this cusp effect. And so it means that this high status data really help us to advance the knowledge on the light hadron spectroscopy. And another example is that BAS3 uses the threshold Lam-C data to measure many different kind of like sigma star states. Okay, let's move to the heavy meson. Heavy meson means that the hadron contains at least one quark of the heavy quark, like C or B quark and so on. The previous knowledge already told us many XYZ states seen in experiment, they are much overpopulated over the 2 quark CC bar states predicted by the quark model. So they mean that many candidates of them should be at least have some exotic nature. One of the famous XYZ particle is the so-called the first XYZ particle X3872, which was observed more than 20 years ago. But however, its nature is still not certain. And you see from the right chart that this its nature of the like DD bar molecular structure or the pure CC bar or compact CC bar QQ bar could have much different prediction on the ratio or its radial decay to psi2s and over the GSI. So this ratio will provide a very concrete discrimination on its nature. So it was measured before by different experiments, but however, the precision is not so good. Recently, RCB observed this its radial decay to psi2s and provides a very nice precision of this ratio, and it can be very well see that it rejects the purely DD star molecule structure and give strong indication that it has a sizable charmonium or compact tetraquark component of this famous X particle. And also another progress from BAS is that the BAS3 did quite a long time to explore more than 10 different hidden charm final states or open charm final states in the E plus E minus direct production. And they found 3 groups of Y states. First is around 4.2 GeV, another is between 4.3 to 4.5 GeV, and also recently they see the Y states above 4.6 GeV. So all these Y states are not very well compatible with the CC bar quark model prediction. So it's, for example, the very heavy Y states like Y 500, 4710, and 4790. So these states are observed in the KKGSI or the DS star, DS star final states, and which means that they could contain the SS bar internal in the structure of SS bar quarks, and also this omega KC1. So it's quite possible that it has this CC bar SS bar internal structure. And also BAS3 using the high static scan data to see many DD bar cross sections, and we see very rich structures. But we will see that fitting to this cross section values will be quite challenging because of there are many states, and also they could interfere with each other. And a couple channel study would be very important and necessary. Another thing that BAS3 showed a very competitive power to measure this Lam-C bar cross-section or DS1 or DSS2. So you see that the cross-section from BAS3 is very priced compared to the previous results from bio using the ISR method. However, we see quite a tension around the threshold of this cross-section. So especially BAS3 disfavor the so-called Y4630, which was seen in the Lam-C bar cross-section. So this means that cross-check is very important in the hadron spectroscopy study. And also regarding to the hidden strange charmonium-like states, so there's another interesting study from RCB. They see this near threshold structure X3960 from the B2 DS-DSK amplitude analysis, and this is a very its JPC is 0++ with very high significance observation, and also very beautiful study from the B2 D*DK amplitude analysis, which simultaneously feed to two channels in order to determine the C parity of the involved charmonium-like state, R state, and they could see at least 3 new charmonium-like states which are candidates for the HC2P, KC12P, and HC3P. So it's very important as in this B-weak decay, we could very well determine the C parity, which is important to determine its to locate its position in the charmonium spectrum. For the ZCS states, it's ambiguously should be tetraquark because it has the open strange and charmonium-like nature. So ZCS already been seen at the BAS3 and RCB, and also BAS see the neutral ZC3985, and also it's natural for RCB also to look for the neutral ZCS 4000, and they really confirm this neutral ZCS state and with the partial wave analysis. And just recently, the RCB see more additional neutral ZCS states by studying this B2 Psi2S K pi pi final states. And this is a very huge sample. And they did a very complicated partial wave analysis and see this that 3 known charged exotic hadrons and also 3 new neutral ZCS states are needed in order to describe wild data. So it's a very nice work. And in addition, the RCB also see open flavor tetraquark, which has different flavor of the quarks of these states, and they did a simultaneous feed to B2DDS pi, and this is 2 isospin symmetric channels, and in the DS pi mass spectrum in both channels, they could see the enhancement around 2.9 GeV, and they firstly observe the doubly charged tetraquark TCS bar 2900, and also its neutral partner. Another site of the heavy tetraquark is the fully charmed tetraquark. The first fully charmed tetraquark is called X6900, and which was observed by RCB and published in Science Bulletin in 2020. And Atlas and the CMS, they also did this double GSI final state study to check the the mass spectrum, and they confirmed this X6900 in double GSI final state. And in addition, CMS observed a new structure X6600 and find evidence of the X7100. It's very interesting. And also, the Atlas and the Bio, they try to look for other double charmonium final states like GSI plus Psi2S or eta C plus GSI. Unfortunately, due to low statics, they don't see really strong observation. So for the Bion sector, RCB observed very nice 5 sharp peaks of the excited omega C states, and this is confirmed in the new RCB analysis of this KCK mass spectrum, and these 5 sharp peaks are confirmed very beautifully. And also, in addition, they see another 2 broad resonance structure, which is the new KC omega C excited states. And also in the B-bion sector, RCB used the KB plus 2 pion and confirm the Chi-B 6100 observed by CMS, and also find the new Chi-B excited states, which very nice work. And finally, about the pentaquark, RCB analyzed the B2 GSI lambda P bar and see a very narrow structure in the GSI lambda final states here. And this is the first heavy pentaquark with strangeness is observed in experiment. In addition, Bio also look for this pentaquark with the strangeness, and they confirm the previous PCC bar S 4459, which was firstly been seen at LRCB using the Chi-B decays to GPSI lambda K. And this was evidence. However, Bio also seen this evidence in another channel is the inclusive 1S and 2S decays. It's a very beautiful confirmation, even it's not a 5 sigma observation. Okay, let's go to my last page. So we see 2 years of exciting period of the new hadron being seen in different experiments, and also especially in light hadron sector, BS3 gave very exciting results on the global like state X2370, and also we see more than 20 new hadrons, mostly exotic hadrons, in different experiments, and it's very nice. And we would be eagerly to analyze new results based on the coming 3 times luminosity upgrade of the BPC2 and also the ongoing LC run 3 and also Bio2 data accumulation. And that's all. Thank you.
Many thanks, Xiao-Rui. You know, it's really nice to see, right? We've been asking for years whether we can see both compact tetraquarks and molecular states, and now it becomes clear that actually we're seeing both. It's,
yeah.
Sure. Can I have questions for Xiao-Rui? I think Louis.
Oh, hi. Wow, that's quite a collection of states. When you quote the significance, are you allowing for the look elsewhere effect?
Yeah, I think this is become more and more popular and necessary in experimental study. So we, at the BS3, at the LCB, at the Bio, I'm not sure Bio because I'm not a Bio member, but at least at BS3 and LCB, this looks LF effect is always been an important way to identify new hadrons.
Okay, thanks. Okay, we take one bit further back. Oh, Ignacio.
Yes. Can you go to the slide 9?
9.
Yes. You said that you performed a PWA analysis, amplitude analysis, right?
Yeah.
What elements you put in this amplitude model dependent?
Yeah, the current practical way to do the amplitude analysis, in order to report the kind of like random structure we have to do with the Bree-Wigner and so on, this kind of assumption is in this spirit is model dependent. Yes.
Yeah, but the only evidence you have is just you put a bright wing and it works. You don't have any other evidence like strong phase variation or only the right Wigner fits well the data.
Yeah. I think in practical many ways of amplitude analysis is doing kind of like a Bree-Wigner assumption, and I think that in the future more cooperation between theorists and also experimentalists, they need more deep cooperation in order to really do a more model independent way. I think that's the future ideal scenario. Thank you.
Many thanks. I think we had one further back.
Okay, I try to answer his question. I think our partial analysis, including all the phases, including all the interference inside our analysis, is not just Bree-Wigner. What I mean, that the partial analysis whatever we used in batch 3 or other experiments. This included all the phases inside of the formula.
Okay. Many thanks. I think we'll carry this one on coffee break. Is there, one from Barney.
This is just a quick one.
That must be correct. It has all these kind of particles are determined like this.
Yeah. You say it's evidence for the 0 plus glue ball, but it could also be a hybrid, could it not? I mean, do you know it's not? How do you know it's not a hybrid?
Yeah, I don't think we cannot reject this assumption or hypothesis. Yeah, I think the scientific way to express this is that it's compatible with the global. Yeah, we cannot really reject other scenarios, I think. Yeah.
Okay, many thanks. Okay, well, we hope to see even more states at the next ICHEP, so many thanks again to Xiao-Rui.
Thank you.
Yeah, and as time is progressing, we are slowly inching towards the latter parts of the conference. And so it's time to welcome the report on IUPAP on Commission 11.
Yes.
And Florencia, you have the stage.
Okay, hello, good afternoon. I'll give a very brief presentation about C11 news for those of you who do not know what C11 is. It's a commission of the IUPAP, who, for those that don't know what IUPAP is the International Union of Pure and Applied Physics. It turned 100 years old 2 years ago. It was built to assist in the worldwide development of physics, to foster international cooperation in physics, and to help in the application of physics towards solving problems of concern to humanity. There's a long mission, and you can find it in the webpage. There are 20 commissions currently. There are 21 groups. One of them on sustainability is new. It was added a year ago. And then there are also affiliated commissions. We belong to the C11 Commission, the Particles and Fields Commission, but also have connections with other commissions that are part and there are associate members of our commissions as well. There are 60 territorial members that are representative of identified physics communities also across the world. And we have a general meeting once a year, usually in October. The C11 mission is to promote the exchange of information and views among members of the international scientific communities in particle physics in all areas, theory, experiment, accelerators, detectors, techniques, etc. We work closely with working group 1, that is ICFA. We also recommend to the union the sponsorship of conferences that we spend some time, and I will tell you more about the conferences later. And then also try to initiate new conferences that might, as the need arises, and then also to ensure compatibility of international conference in this field and to discourage clashes or incompatibilities of dates, for instance. We also try to work on promoting closely with IUPAP to promote the free circulation of scientists and to assist conference organizers in ensuring that there's a free circulation of scientists and resolving any potential infringement. And then we also organize every 2 years awards, and these are the C11 awards that we will give today. These are currently the C11 members. This is for 21 and 2024. The membership will change in October. This is my last C11 presentation, and my term ends in October. And then there's going to be a new chair that will be elected in October at the General Assembly. Now, from IUPAP News, I only have one slide and two things that I wanted to mention to this audience. One is that just to put some attention to the International Year of Quantum Science and Technology. That is 2025. This is a year that has been proclaimed by the UN. as the year of International Year of Quantum Science and Technology. You can find more information in that website. This was led by IUPAP and includes many C11 relevant organizations as partners, as you can find there. There's also now declared in 2024 to 2033 the Decade of Science and for Sustainable Development. This goes beyond physics. It also includes the social science, etc. This was also the approval came also as a sequel of a very successful year of basic science for sustainable development that was in 22 that you can find here, in which IUPAP played also a key role. The first 2 years of this decade are dedicated to form this Earth Humanity Coalition, in which will serve as an activation and expansion, and then include science, as I said, from all fields, humanities and human science and natural science. If your organization, institute, or university is interested in this is now a good time to join, and there's more information in there. C11, the C11 community has the potential to contribute enormously to both year, to the decade and to the year, and we encourage you to look at this and see if you are interested and to collaborate there. Okay, so now on the conference side, so these are, I want to briefly tell you what we do and the next conferences, the upcoming conferences that C11 and IUPAP will be sponsored. First, I want to let you know that, I mean, the conference is sponsored by IUPAP. I categorize usually by type A, B, and C. And with D being also workshops that are for developing countries. The type A and B and C depend on the scope of the conference and also the amount of people that attend the conference. This ICHEP is a sponsored conference from IUPAP, and it is type A, because it's the largest conference that our field has. To be able to request support, the conferences are required to have a significant scientific value. They'll also be truly international in the sense not only in the participation, but the location has to rotate across countries and continents. There's a minimum participation of women in the organization and also attending, which is quite low in my opinion for our community. There's also a host country declaration that individuals will not be excluded solely on the ground of origin or citizenship. The fee has to also make sure, we have to also make sure that it goes beyond that it can be accessible for all countries and then all stages of the careers of the participants, and then that there's also a code of conduct that includes also to adhere to the IUPAP anti-harassment policy. In 2024, these were the funding support for Tab A, B, and endorsement are this conference here. This is one of the conference that I said it was Type A, is ICHEP. In 2025, then there's Lepton Photon, Type A, and then Type B, LHCP, and then there's 2 conferences that are endorsed. Now, for 2026, how it works to get sponsorship and endorsement for 2026, usually the application opens in January and it closes in June 1st of the year previous to the conference. So the applications, and this is for applications for financial support. Applications for endorsements are always open and it can be asked for endorsement at any time during the year. The application should contain information about the participation of institute, the local organizing committee, cost, etc. And then if you want more information, then there's the conference guidelines in this link. ICHEP and Lepton Photon are different. They are actually, we look at the bids for ICHEP and Lepton Photon and NTIP, the instrumentation conference, 2, 3, or 4 years before the conference, because we want to ensure transition between the organization of these major conferences and make sure that there's enough transfer of knowledge between the organizations. So during ICHEP 2024, C11 reviewed applications for TIP 2026, lepton photon 2027, and ICHEP 2028. And this is what we agree, that the TIP 2026 will be hosted in Mumbai, lepton 27 in Shanghai, and ICHEP 28 in Bangkok, Thailand. This is a list for, but next year there's also a lepton photon that is going to be in Madison, Wisconsin in the US. The next ICHEP, as you will see later, a presentation from Rogerio, it will be in Natal, Brazil, and this is new. Bangkok and Shanghai are new here, and TIP Mumbai, that is new as we have voted on Friday. Okay, so now on the Early Career Scientist Award. So the C11 awards 2 Early Career Scientist Awards every 2 years. This is done this is given to 2 outstanding early career scientists in theory and in experiment. We review many applications every 2 years, and it's probably the highlight of the commission to do the review and be exposed to huge and enormous range of talented young people and in all areas of our field. So this year, it is my honor to introduce the 2 awards. I'll go first to the first one, that is Jennifer Ngadiuba for co-designing, development, and deployment of novel machine learning techniques to address complex elementary particle physics challenges with focus on ultra-fast real-time data analysis on hardware triggers and for model agnostic searches for beyond the standard model physics signals at the Large Hadron Collider. So, Jennifer. And we have to look it, and this is the part, so and you have to look there. Oops, and you have okay. Thank you. And Ian Moult for the invention of novel jet substructure observables, which have had a direct impact on the Collider physics program, and for developing new effective field theory techniques to enable high precision calculations, including in multi-pronged kinematics and subleading in soft and collinear limits. And you hold this. Thank you. And following, we have a presentation from both awardees. The first one will be Jennifer, and then following will be Ian. So I leave you with them.
She still needs the microphone, but she's almost ready.
Okay.
Jennifer, the stage is yours.
Hello, everyone. I'm very honored to be here today as a recipient of this award. And also, I'm very pleased to introduce you to my research focused on transforming the LHC physics program with AI. I would like first to thank the IUPAC committee for selecting me for this award, and also the conference organizers, and the team of excellent scientists that I had the pleasure to work with in these last few years. So at this conference, we discussed a lot how probing the fundamental structure of nature requires complex experimental devices, large infrastructures, and big collaborations. And these are expected to grow even further in size and complexity in the near future. So with a large discovery potential also come data challenges. In fact, we have to deal with increasingly complex data, both in volume and dimensionality. And this diagram shows the streaming data rates and the latency requirements for different particle physics experiments. And you can see how the LHC is here at the corner and beating also industry standard, also in terms of sizes of data sets. So in this picture, we need to develop efficient and accurate data processing pipelines. We also have to face challenges in simulating expectations for what experiments may observe. And we also need innovative data and discovery-driven approaches for physics analysis. So at the LHC, we deal with extreme data rates of petabit per second. In fact, this is due to the fact that we collide protons at an extreme frequency of 40 megahertz, and then each collision creates thousands of particles, and we have high-resolution detectors with up to 1 billion channels to record these particles. So we have a data reduction workflow in place, which is implemented through multiple filtering stages. A first stage implemented on FPGA hardware with microsecond latency, and then another stage implemented instead on commercial CPU or GPUs with 100 millisecond latency. And these are the data, after these filters, these are the data that we store and analyze offline. So at the end, we perform physics discoveries with a very tiny fraction of the events, while the rest is lost. And this worked very well when we know what we search for. For example, it worked for the Higgs boson, and it also works for many motivated BSM theories that we probe, and we put limits, stringent limits today. And this works because we are guided by strong physics assumptions throughout the full analysis workflow, from data reduction to the data preprocessing to the final statistical interpretation of high-level features. However, nature might be different from all of this, and it might be that we're not looking in the right corner because we might have not imagined yet how new physics look like. So we started thinking about complementary approaches in which we go back looking at data with no signal hypothesis and eventually remain surprised, as if we identify an anomalous signal, we can formulate an alternative hypothesis to then be tested with the new data and standard techniques. So this approach is what we call anomaly detection. Today, we can implement anomaly detection efficiently with AI. In fact, machine learning is used in particle physics since the 80s. It was shallow networks back then. But things became more exciting over the last decade, where we've seen a rapid progress guided by technological breakthrough that led to a revolution in this area. So we are now in the era of deep learning. And we can use deep learning, indeed, to implement novel data-driven search strategies like anomaly detection, which consists of identifying in data sets rare events which deviate significantly from the majority of the data and do not conform to the normal behavior. So the normal behavior, so everything we have to do is to learn the normal behavior, and this can be done through a neural network by training it in a data control region populated by standard model events. So we started testing this approach with one of the most studied physics cases, the search for a dye-jet resonance. We train a neural network to learn the standard model QCD background in a control region, so dominated by single quark or gluon jets, and then tag each jet as anomalous in the signal region with no assumption on how it looks like. There are many different ways in which we can obtain this, achieve this goal. These methods can have increasing model dependence, depending if it's supervised, weak supervised, or semi-supervised. And all these methods also have nice complementarity. So in CMS, we implemented 5 different of them in this first search looking for anomalous dye-jet events, which was just released this year. So we probe the discovery potential of these methods by injecting a signal of varying cross-section in background Monte Carlo and then calculate the p-value. And we compare then this p-value with the one that you would obtain with the traditional, more traditional searches. And we can see that we have a large discovery potential improvement with respect to standard analysis methods, and this happens also for a broad range of signals. Here is just one signal, for example, but we probe many different ones, and we observe the same behavior, so demonstrating a good generalization of these methods. However, this analysis is performed offline, and considering that we reject a lot of events and only a tiny fraction is what we actually analyze, the question is if new physics is even there, as the event filtering starts very early in the data processing. We started thinking on how to address the challenge as early as possible in the data reduction workflow, and in particular at the hardware trigger level. This is particularly challenging if we want to use neural networks, because nowadays deep neural network can become relatively large, such that memory and number of operations required for the inference can easily explode. While in the hardware trigger, we have strict constraints in terms of latency of few microseconds, and also scarce resources on the FPGA hardware that we use to implement our algorithms. So to fit the neural network here, we built our own custom tool called High-Level Synthesis for Machine Learning, or HLS4ML, which is a tool to efficiently program the FPGA hardware for neural networks with experimental constraints in mind. Basically, we map machine learning models developed with the standard APIs to circuit through a code that we write, which is highly optimized to meet our constraints. It was interesting to see how this, let's say, cutting-edge tool sparked the interest of industry. So in the past years, we had the chance to collaborate with Google, Siemens, as well as Volvo and others. So it was a very interesting product that we could create. Thanks to HLS4ML, CMS had the chance to establish a new trigger paradigm with the sub-microsecond autoencoders for anomaly detection. So we train an autoencoder in a control region populated by standard model events, and this neural network runs in only 50 nanoseconds and occupies a very small fraction of the FPGA hardware where the full baseline trigger menu is implemented. This algorithm called Axolotl is now taking data after several years of development from many different people. And it's nice to see that it's actually triggering on unique events which would otherwise remain untriggered or lost, so demonstrating nice complementarity with the baseline menu. And here you can see an example of an otherwise untriggered high multiplicity event. So the CMS anomaly detection trigger is just the first step towards a revolutionary new paradigm for data acquisition at colliders and also beyond, as demonstrated by the growing number of research articles that aim at implementing AI really at the edge of physics experiments. In fact, the ability of doing so is a game changer, and ICHEP is actually at the forefront of the R&D in this direction. In fact, the requirements for AI in particle physics go far beyond industrial and commercial applications. We need the speed, throughput, fidelity, interpretability, and reliability. And demonstrators like the CMS anomaly detection trigger today are crucial to learn now lessons for the future. So it was very exciting to see how the importance of this effort was recognized when it was announced early this year that the private donors, Eric and Wendy Schmidt Foundation, found a CERN project that will enhance the physics reach of the ATLAS and CMS experiments at the ILUMI LHC and also beyond, using novel technologies, and in particular the ones that I just described in this talk, among others. So the Next-Gen Triggers project will mark a new chapter in high-energy physics, leveraging upgraded event selection systems and data processing techniques to uncover a realm of discoveries. This brings me to my summary. Our scientific mission is beautiful and engaging. However, answering to fundamental questions about the universe with very advanced particle detectors come with enormous challenges due to the large volume of data and experimental system constraints. AI offers a solution because of the scalable capabilities, so allowing us to accelerate time to discovery, but not without an intense effort to change our approaches today at every data processing stage. It's crucial to promote interdisciplinary collaborations, to invent solutions that would not be available in the world otherwise. And these can then be injected back into society as our technological innovation is fueled by our unique physics requirements. Thank you.
Many congratulations again, Jennifer. Thanks
so
very
much.
Thanks very much for this very nice presentation.
Thanks.
Okay. And we'll now pass to our second award winner, Ian Moult, who's also going to tell us about his work.
Okay, so thank you very much to the IUPAP for this award, and also thanks to the organizers for giving me the opportunity to talk about my work, as well as to visit Prague. So today what I'm going to be telling you about is some recent progress in trying to better connect certain ideas in formal quantum field theory with real-world collider physics, for example, at the LHC, with the ultimate goal of trying to improve our ability to search within and beyond the standard model of particle physics. And so throughout, I'll try and really emphasize the interplay of theory and experiment in achieving this goal. So as everyone is familiar, the kind of big picture goal of collider physics is to try and learn about the underlying microscopic interactions of the quantum field theory governing nature by looking at macroscopic correlations in the energy flux which comes into the detectors. And so an early and very famous example of this is using the three-jet topology to discover the gluon. And so from a modern perspective, this is quite simple. You can kind of see it by eye. But as we go to the LHC, in either proton-proton or heavy ion collisions, we produce these extraordinarily complex, very high multiplicity collisions. And so in these cases, it becomes much harder to link the kind of patterns in the energy flux that an experimentalist might observe in their detector to the underlying quantum field theory. And so this is particularly true as you start to try and ask more and more subtle questions about the underlying quantum field theory. For example, questions about the dynamics of confinement, or for example, about properties of the quark-gluon plasma. And so this is, in fact, quite analogous to the situation in cosmology. And so the way we kind of want to think about it is we want to infer the kind of microscopic or early time physics from the asymptotic or late time energy flux. And so as a theorist, what this really requires is the development of very specific field theoretic techniques to interpret subtle correlations in terms of the dynamics of the underlying quantum field theory. And so in the formal theory world, there's actually been a tremendous amount of progress in this area recently by trying to abstract from real-world colliders and real-world detectors, which are extremely complicated, to kind of toy colliders and toy detectors, with this as being the kind of theorist's picture of what's going on at the LHC. And so one thing that's been learned is we now know how to write down operators in quantum field theory which behave exactly like detectors. And so you can think of, for example, a detector or an operator in quantum field theory that behaves like a calorimeter cell, so that measures, for example, energy. And you can do this for other properties of interest. And so this is very nice because it allows us to formulate collider physics questions in terms of certain correlation functions of these operators. And so what we've developed are very powerful techniques to be able to manipulate and compute with these operators, which allows kind of new ways of understanding and of computing observables in collider physics. And so I should say that this builds on early seminal work of Sturman and Ellis and collaborators, which appeared actually right after the introduction of asymptotic freedom, and whose history is kind of very interesting and interwoven with the history of QCD itself. And so in the last year or so, this has become extremely interesting because there's been the first actual measurements of these very nice correlation functions at hadron collider experiments. And so this has been at both particle physics experiments, such as CMS, but also at nuclear physics experiments, such as STAR, and even reanalyses of old Aleph data shown here. And so the reason why this is particularly exciting as a theorist is it builds a very nice bridge between these nice theoretical ideas and real-world experiment. And it also allows the opportunity to apply some of these nice techniques to think about collider physics in a different way and to apply some of these powerful and very beautiful theoretical techniques to describing real-world data. And so what I want to do is just to kind of highlight some of the new ways that these techniques give about, or for thinking about collider physics data. And so the first very nice example, which came out of thinking of the operators, or thinking of detectors as operators, is that these detectors actually admit so what is referred to as an operator product expansion, but you can alternatively think of it just as a kind of Taylor series for detectors. And so if you bring two calorimeter cells very close together in angle, it turns out that you can expand them over some more general abstract set of operators. So the exact definition of what this means doesn't matter, but the only important thing is that the angular dependence, i.e. the separation between the two calorimeter cells, appears out front in this very nice scaling or power law behavior. And so what it says is that if you measure correlation functions in the energy flux, you can actually, by looking at this power law, identify certain critical exponents of your underlying quantum field theory. And so this is a kind of completely generic prediction in any quantum field theory, and it was made about 15 years ago now. And so there's this kind of famous exchange between David Gross, Polchinski, and Maldacena when this was first being discussed, by saying there's a huge amount of collider physics data. Why don't people go and look for this kind of universal property of quantum field theory? And Maldacena's response, which is exactly transcribed, is kind of people haven't thought about this. They should go do it. And so this is something which actually took over 10 years to do. And so very excitingly, this was actually done by all the different collaborations in the last year or so. And I'll highlight in particular the measurement of CMS at very high energies, which was led by Meng Xiao and her group. And so you can see these beautiful power law scalings, just like you have in critical phenomena, as a function of the angle between the two calorimeter cells. And so I should emphasize that these are purely quantum mechanical scaling, so they're really critical exponents, and these would be completely flat in a classical theory. And so this is very nice for probing the kind of precision structure of quantum field theory, and it also, I think, really highlights the power of colliders for probing completely generic phenomena in quantum field theory. And so this measurement was actually highlighted in the Advances in Conformal Field Theory at the String Theory Conference, which I think is a very promising thing for the interplay between theory and experiment. But of course, at a practical level, what can you do with this? So one of the things you can do with this is if you can accurately measure the slopes, so these are proportional to the value of the coupling in your theory, and so you can actually measure it accurately enough that you can extract the value of the strong coupling constant at about 4% accuracy. And so this is not the world's best extraction, but it's the best from jet substructure, and it kind of opens up a new promising way of performing these measurements, just like how you measure critical exponents, for example, in the Ising model. And so I think it also really brings jet substructure into the kind of precision era, which is extremely exciting. And so beyond scaling, what can you do? So if you look in, for example, the CMB, often what you want to study are higher point correlation functions. So these really map out the kind of nonlinear interactions in your theory and allow you to, for example, distinguish between models of inflation. And so all the nice progress in perturbative scattering amplitudes has enabled us to be able to actually compute higher point correlation functions of energy flux inside jets at the LHC. And these have a beautiful mathematical structure in their own right, which unfortunately I won't be able to go into in this short talk. And so instead I'll just kind of highlight with a picture how we can actually measure, for example, 4-point correlation functions inside jets. So this is a calculation over here, and then a measurement over here by these people here. And so you can see that you can really map out the internal structure of a jet with kind of unprecedented resolution, and you can really kind of map out the interactions of QCD and ultimately use this to better understand the standard model. And so I'll just conclude with one example of how this new way of thinking can be applied to more complicated systems. And so this is a measurement which actually just came out last week. And so one thing which you can do is to measure these correlation functions in heavy ion collisions to try and probe the nature of the quark-gluon plasma, which this is my little illustration of. And so the very interesting thing is that if you measure these correlation functions as a function of angle, as you move them apart, it drives back the interaction into the plasma. And so what you get is, at very small angles, you get a kind of vacuum scaling behavior, which you can compute in perturbation theory, and gives this nice power law, which I discussed earlier. of these kind of critical scalings, and then you expect some abrupt transition when this object kind of enters the plasma. And so you can see exactly that effect right here in these lead-lead collisions, and this is in the ratio. And so you see this very large enhancement, which is due to the interactions of the quark and gluon with the finite temperature plasma. And so this really gives us a very nice theoretical handle and a lot of nice data for theorists to play with to try and better understand the interactions of quarks and gluons with the quark-gluon plasma. And so just to summarize, so on the theory side, there's been a huge amount of progress in the theoretical characterization of asymptotic fluxes in quantum field theory. And this is very nice because it has direct application to collider physics, because this is exactly what one does in collider physics. And so this will really provide new ways of thinking about and computing collider physics observables. The scaling and shape dependence of these correlation functions can be directly measured inside LHC, which is just a development which has happened in about the last 6 months. And what's most exciting, at least to me as a theorist, is that this really provides the opportunity to use these kind of theoretically beautiful objects to learn about real-world physics in colliders. And so I just want to conclude by thanking all my collaborators, in particular my longtime collaborator on this work, Professor Huajing Zhu, as well as a number of students, in particular Yibei Li, Hao Chen, and Xiao-Yuan Zhang, who all actually started working on this as undergrads, and they're now going on to their postdocs, so they've worked on this for about 5 years, and did an immense amount of work in really making it into a reality. So thank you.
Okay, so we are coming to the last part of this block, and this will be about poster awards. So let me just give you a few details on the poster sessions. We had about 282 fantastic posters. They were hanged and displayed for 3 days. And given the large amount and large number, we kind of set it up in an unusual way, asking people to present one at a time on the first and the second day. So we had two sessions, and this was really to give the people the deserved space and attention to their well-prepared posters. So as you can see, there's a lot of space, but when the poster session started, the space was quite cramped, and you experience it also, that there were a lot of engaged discussions, people exchanging. This was really, really great to see, and good moments, people making new contacts and hopefully spurring to some collaboration afterwards. For the review and judgment of the posters, we had about 180 posters which were eligible for poster awards, and the condition was that they will be uploaded in advance to Indico to allow our judges to go through it and review it. So the judges were looking for well-crafted posters that were explained with enthusiasm, and we were also asking what was the contributions in these particular posters. So just here is a snapshot of the numbers. The poster spanned the entire theme of the conference, so it was quite a difficult and challenging task for the judges to make a selection. Just to point out, the 56 posters were from the operations of the existing detectors. Before we go to actually handing over the awards, let me give a few thank yous. So first of all, the first thank you goes to the local organizers, Peter and Yarda, who organized the layout of the session and also organized the review with the judges. Then the second big question is to the reviewers. We had about 15 reviewers that were going around the posters and talking to the participants. Huge thank you to the people that were actually preparing and designing their posters. They were all excellent. And finally, thank to you to coming there and making the atmosphere lively. And at the end of the day, the conference center had to many times ring the gong to push people outside. So it was really lively atmosphere, and people would have stayed discussing their favorite topics probably for another hour if we didn't have to leave. And now we go to the poster awards. So we are awarding 7 prizes. The people will receive diploma, but also some monetary award. And we start with Francesco Faldi, who I would like to invite on the stage, who who prepared this magnificent design where a fireball is flying towards the Earth, and the poster award was unique properties of daily proton fluxes up to 100 GeV. Thank you very much. Next, I would like to invite Rhiannon Suzanne Jones for the poster Neutrino Interactions Measurement Capabilities of the SBND Experiment. Applause for Rhiannon. The third poster award goes to Xiao-Rui Lyu, who gave an in-depth discussion and explanation of his search for heavy scalar resonances in the 4 lepton final states in the CMS experiment. Then I would like to welcome on stage Tanima Mondal, who prepared a poster on the analysis of the electron-neutrino event sample at intermediate water Cherenkov detector at the Hyper-Kamiokande experiment. Congratulations. On the outreach activity, David Borgelt prepared a poster, International Masterclasses in Particle Physics, expanding geographically and broadening in scope. Unfortunately, David cannot be with us because he fell sick during the conference, but I hope he is watching us online. But we will clap anyway. And then we had a poster from Renske Vierda. Please come to the stage now. And this was on Run 3 improvements in the Atlas online luminosity measurement. Congratulations. And final award goes to Yung Wu on the parameterization of the PMT single photoelectron response shape variance with linear models. And you can notice that he actually figured out a way how to make backup slides for a poster, which is quite unusual. So congratulations. So congratulations to everyone. We have to take one obligatory photo, so please look at our photographer here. Excellent. So applause for everyone, and to everyone who contributed, prepared posters, and also came to the session. And now we can break for the last coffee break of the conference.